Okay, let's get started with problem 3.4 now from Wald's General Relativity, where in 4a he wants us to show that in 2 dimensions the Riemann tensor takes the form of the Ricci scalar times this anti-symmetrized metric thing. And the hint is to use the result of problem 3b to show that this spans the vector space of tensors having the symmetries of the Riemann tensor. Okay, so we can go ahead and do this. Just to get started, let's write this out explicitly. We want to show that R, A, B, C, D equals R, the Ricci scalar, G, A, C, G, D, E. Oops, this is a mess. And yeah, these are anti-symmetric brackets. They should be square brackets in 2D. And so more explicitly, this is going to be something like R over 2 times GAC GDB minus GAD GCB. So we're going to do what the hint says here. So let's define a new tensor like this. Let epsilon A, B, C, D equal just the part of what we're trying to show here that has the metric. So we'll drop the Ricci scalar there, and we'll just let it be this G A C G D B. Okay. So expanding this more explicitly, obviously we have 1/2 GAC GDB minus GAD GCB. So let's start by looking at the 3 symmetries of the Riemann tensor here and seeing if this tensor also satisfies those things. So we can look at epsilon, say BACD. So this is going to be 1/2 GBC GDA, pardon me, minus GBD GCA, basically just flipping the B and A in the above. So now let's rewrite this with a minus sign pulled out front, so the inside gets flipped around. We get GBD GCA minus GBC GDA. From here, we will use the metric symmetry. Namely that GAB is the same thing as GBA. So with this, we have minus 1/2. Let's see. GAC GDB minus GAD GCD, which is nothing other than the negative of epsilon AB CD. So that's one symmetry of the Riemann tensor that we've checked that it has. Okay, so how about doing the same thing but with the last 2 indices instead of the first 2? So let's go ahead and check that. So we'll be thinking about epsilon A, B, D, C now. So we'll pull the minus sign out front again. And actually, let's see if I can scroll up so that we can see the original. Probably not. I'm going to copy this. well, that doesn't work. That's fine. Okay, so we'll just rewrite this with the minus sign. So we get GAC GDB minus GAD GCB. And that is indeed also negative epsilon ABCD. So that one comes out a little more quickly, and that's nice and easy. So we checked the second symmetry. And now let's check the swap symmetry, I think they call it. So we're going to have CD, AB. So interchanging the first two indices with the last two. Okay, so we can just write this out explicitly based on what our formula gives us. GBD, GCA, minus GBC, GDA. So again, we're going to use the metric symmetries. Or metric symmetry, I guess I should say. So we can rewrite this as 1/2 GAC GDB minus GAD GCB, which is exactly epsilon ABCD, so no minus sign this time, which is what we expect for a tensor with the symmetries of the Riemann tensor. Okay, so we've checked now, oops, that's not a 3, the third symmetry. Okay, so we know from the previous problem the Riemann tensor has independent components. So in 2 dimensions, we get 4 minus 1 is 3 over 12 equals 1 independent, component. So if there's just one independent component, and we know that the Riemann tensor and our epsilon tensor have the same symmetries, we're able to say, thus, RABCD equals alpha times epsilon ABCD, where epsilon is some constant here. Or where alpha is some constant here, sorry. So we can write this explicitly as alpha over 2 GAC GDB minus GAD GCB. Okay, so now if we go from here and we want to contract over the indices B and D, we will get the Ricci tensor RAC on the right-hand side here equals alpha G BD or DB, whatever you want to call it, times epsilon ABCD. So if we actually write this out explicitly here, we get like a GAC, and then we get like a trace of the metric here, the GDD minus, this is going to be a delta A B GCB, and this equals alpha over 2. The trace of the metric is going to give us 2 in 2 dimensions, so we get 2 times GAC minus delta AB on this minus GCA. But thanks to, well, we'll write it GCA, but thanks to metric symmetry, this is alpha over 2 to GAC minus GAC. Or in other words, RAC equals alpha over 2 GAC. So now we can contract again over A and C, and we get the Ricci scalar on the left-hand side. And this is going to be GAC alpha over 2 times GAC. So again, this is like the trace of the metric here. We're going to get 2 in 2 dimensions, which cancels out with that 2, and we get alpha. So we're able to show that this constant alpha is R, the Ricci scalar, and therefore we've proven that our ABCD in 2 dimensions is the Ricci scalar times our tensor epsilon, which I'll be writing as this anti-symmetrized metric thing. Again, just because that's how it is in the problem statement. So that's what we've shown. Okay, let's have a crack at 4b now. So he says, by similar arguments, show that in 3 dimensions the Weyl tensor vanishes identically. In other words, for n equals 3, equation 3.2.28 holds with c equals 0. So I put equation 3.2.28 down here. Okay, so 3.2.28 is basically saying something along these lines, that R A B C D equals C A B C D plus something else which we'll call chi A B C D. Now chi is going to have the same symmetries as the Riemann tensor. The reason for this is because so does C, the Weyl tensor. So yeah, if the Riemann tensor is going to be a sum of these 2 tensors, one of which has the same symmetries, the second one also has to, obviously. So these tensors, using the results from the previous problem, such tensors have 3 squared minus 1 over 12 independent components in 3D. So this is what, 9 times 8 over 12, which is 72 over 12, which is 6. Now, okay. We know that the Weyl tensor is trace-free in all indices. This means that Ricci tensor RAC is going to be equal to chi A, B, C, B, because the Weyl tensor term goes to 0 with that trace, right? So this adds three times 2, so 3 for the first index and then 2 for the second. So this means number of free components is then 0. It's because we've shown that we have 6 independent components and 6 restrictions here. What this means then chi ABCD is our ABCD in n equals 3. So then we can go back to our original equation, right? So let's substitute in our ABCD here, because we've shown that that's what chi is. We can cancel on both sides, and this implies that the file tensor equals 0 in n equals 3.